Today we're going to start our new and last unit of the year. We're going to be talking about exponential functions, and today we're going to do an intro and look at graphing. So this video might be a little bit longer than what we've been doing lately, but it's really important information. Okay, so the first thing that I want to look at is we're going to compare a linear function and an exponential function in order to see what the differences are. So I'm going to go ahead and complete this table. I'm completing this table by just substituting anywhere there's an x, whatever the x value they give me. So the first one is -2. 2 times -2 is negative. Different color here. -4, -2, 0, 2, 4, and 6. So all I did was anywhere that there was an x, I substituted the x value that was given to me to get my new f of x value. So now let's look at g of x, this exponential function. And if you notice, one of the reasons why it's an exponential function, look where our x is. It's not in line with our coefficient, but it is our exponent. So that's kind of where you can get the idea that this is an exponential function because our variable, our input value, is in the exponent. So -2. If you remember when we were doing exponents in our polynomials and exponents unit, if we have a negative, that's really flipping it. That's doing the reciprocal. So that's saying 1 over. So 2 squared, so 2 times -2 is what we're talking about, is really 1 over 4, because 2 squared is 4, so that would be 4 to the -1 power, which would then be 1 over 4. That's how we're getting that information. So 1/4, -1 would be 1/2. 0 power, anything to the 0 power is 1. Anything to the 1 power is itself, so 2 to the 1 power. 2 squared is 4. And 2 cubed is 8, so 2 to the 3rd power. What I want you to do is look at the differences that we've got in numbers. Look at the y values and how they change. What does our rate of change look like? What I'm going to do now is I'm going to go ahead and plot these points. So I'm going to go ahead and make my linear function in this pink color, and we have -2, -4, -1, -2, 0, 0, 1, 2, 2, 4, 3, and 6. So we have this straight line that's forming our linear function. Oh, right there. See if I can get a good line here. Not the best. That's better. So this is our f of x. Now let's plot the points of g of x. I am going to switch colors. So at -2, it was a positive 1/4, somewhere around there. At -1, it was about 1/2. At 0, it was 1. At 1, it was 2, so they share a point there. 2, 4 shares another point. And 3, 8. So this one looks more like, that's a really not the best. See if I can do a better one. Something along the lines of that. That is our exponential function g of x. So there's some similarities and there's some differences when we're talking about exponential functions. And later we'll talk about things that grow exponentially. And when we talk about things that grow exponentially, that's when we're looking at graphs like this. So some of the differences you might see is that the linear line, the straight line in red, increases at a constant rate of change. That's our slope. That does not change in a linear function. And the exponential function does not grow at a constant rate of change. In fact, it grows constantly different. And then a couple of things I wanted to talk about, I'm going over my notes here. One thing to look at on the exponential function, if you put these tables in, or you put these points in, or you can use your y equals sign and go ahead and put 2 to the x power, so you would hit y equals 2, and then the little up arrow button that's right above the division sign, that's the power button, and then you would hit your variable button to put in x on the power. And you can go ahead and go to your table and look at your points. And one thing I want you to look at, does it ever cross the x-axis? Meaning, is there any zero or negative numbers in this exponential function? And what you should see is that it will never cross the x-axis. It will never be a negative output. When you're squaring something or you're multiplying something by itself like that, it will never be negative as far as this function, this exponential function. So, one thing I want to also look at is on the graph, if we, as x increases or decreases, what is happening to 0? What is happening to our y value when you're looking in the graph? And when you see that, you should see that as x decreases, meaning as it gets smaller and we go to the negatives, that the y value increasingly gets smaller and it gets really close to 0. But it will never equal 0. Okay, so exponential functions have the following unique characteristics. So this is when we really start getting into what is an exponential function. So it's written in the form of y equals a times b to the x, where a cannot equal 0, b is greater than 0, and b cannot equal 1. So b cannot equal 1. A can't be 0, b has to be greater than 0 and cannot equal 1. So it can be something other than that, but it cannot equal 1. The graph of an exponential function increases or decreases rapidly. That's the exponential part. An exponential graph will always have a horizontal asymptote. So that's kind of a weird word. A-S-Y-M-P-T-O-T-E, asymptote. I apologize for the bell. The asymptote is the value that f of x approaches as x gets either very large or very small, and can be thought of as an imaginary line or almost as a barrier, as it will never cross that asymptote. So, based on the description of an asymptote, what appears to be the horizontal asymptote of the g of x? We've talked about it a little bit ago, but our asymptote for this one would be y equals 0, or the x-axis. And that is because as it increasingly approaches, but it will never cross. So that is our asymptote. It will get extremely close, but it will not touch that asymptote. It's kind of like an imaginary barrier, an imaginary line that kind of exists with the exponential functions. So, in 1 through 3, an exponential function and its graph are given. Sketch a line to represent the asymptote and write the equation of the line. If necessary, use a graphing calculator to help. So when we say use a graphing calculator to help, that means look at it to see where does it get really close, but it never crosses. So if we're looking at f of x equals -1 times 3 to the x power, so this is our y equals a times b to the x. So a is -1 and b is 3, which meets the rules. You can see this line gets really, really, really close to y equals 0, or the x-axis again. So the equation for the asymptote would be y equals 0 again. And that is a pretty common one for exponential graphs, but it's not necessarily the only one. So y equals 0. I'm going to go ahead and skip 2 because once again that's y equals 0. But on this one, looking at this graph, if you notice, it's not right at the axis. It's a little bit higher. And you can see it increasingly approaches this line right here. So we know that's our asymptote. So our asymptote is really this line. And pay attention when you're looking at your axis that it's not counting by 1, so even though it's one little square up, it's really at 2. So our equation for our asymptote here is y equals 2. So that is what an exponential function is and what an asymptote is, because that is going to be a big part. So we're going to do a quick example, hopefully a quick example, on our notes here to kind of help us understand, and then we'll dive into the graphing. So Sean currently has $10 saved and would like to build more savings over the next several months. His 2 potential plans for saving are described below. Use the 2 options to complete 4 through 7. So option 1, depositing $20 each month into a savings, where y equals 20x plus 10, where y is the total amount and savings and x is the number of months. Option 2, doubling the amount in savings each month, y equals 10 times 2 to the x, where y is the total amount in savings and x is the number of months. So, what type of function is represented in each option? Well, I'm hoping you can kind of already see that option 1 is linear, and number 2 is exponential. So we're going to complete the graphs. So using the equations in the little squares up here at the top, we're going to fill in our tables, just like what we did in our beginning. So we started at 10 for option 1, and every month we add 20. So 10 plus 20 is 30, 50, 70, 90, 110. Okay, option 2, we're doubling the amount every time that's in the bank account. So he started off with $10, so doubling that, that would be 20. Well, doubling that, that would be 40. Doubling 40 would be 80. Then 160. Then 320. So let's graph what we can. So at 1 month, he had, at 0, he had 10. That's where we're starting. Let's do, I should have done this a different color. Sweet help. That was 10, 20, 40, 80, 160, 320. Go ahead and graph the purple one, our linear function. We're adding 20 each time, so at 1 he had 30. And you can kind of see the pattern that we've got going on here. Linear function. Its rate of change is constant. It stays the same each time. So that means it's a straight line. Like so. And then now let's graph our second one. So it also starts at 10. And then at 1 month, he's also at 20. And then at 2 months at 40. 3 months at 80. 4 at 160. And we don't have a big enough graph for our next point. So that's kind of the line. Ooh, that is not pretty. That's better. So that is our exponential line. Now, if you notice, well, it wasn't a great line. Some months it is below our linear function, but other months it goes above. I'm just not having any luck with this, so you can see not the pretty line. There we go. So until we get to about month 3, you see that the option 1 might have more money, but because we're doubling over time each time, eventually, and actually pretty quickly, option 2 would get more money. So which option will result in Sean saving more money? That would be option 2 after month 3. And then if you want to talk about the differences. But let's go ahead and talk about graphing exponential functions. So this is where it gets kind of interesting, but you can always double check yourself by putting them into your calculator and seeing if it matches. So every exponential function in the form y equals a times b to the x power will pass through the point 0a. So 0 and then whatever your a value is. Therefore, a will always be the y-intercept, and it's often referred to as the initial value. This is the beginning amount. Not very different from a linear function's initial value where it was the y-intercept as well. So in 1 through 4, plot the y-intercept, then use graphing calculator to sketch the rest of it. What we're doing on that one is it's just really asking us to use the function, find a couple points by substituting an x value into the function and then figuring out what the output is. So when you're doing that, you can really just use your calculator to help you. I highly recommend it, and you can look at tables to help graph it. But I really want to go ahead, I'm actually going to go ahead and skip this for time reference, but I want to focus on domain and range. So domain and range. And part of it includes our asymptote. So in 6 through 8, identify and write an equation for each graph's asymptote. Then use the asymptote to help you determine the domain and range of the function. Hence, the asymptote will provide the boundary for the range of the exponential function, meaning at one point it's either the top, its maximum value, or its minimum value. So looking at number 6, we can see that it's approaching y equals 0. It's approaching that x-axis. So I've got arrows on both sides. It's going on forever. My domain is all real numbers. But my range, I know that it cannot go anywhere near 0. So instead of y being greater than or equal to, it really is greater than 0. Y is greater than 0. Looking at this one, it's also approaching y equals 0 at the top, though. So that means even though that's all real numbers again, it's going to be y is less than 0 because it can't equal 0, and it's not going to get on the other side. Asymptote here. Now we have a real world scenario that confines our domain as well. So once again, y equals 0. And with it only being positive, and we have a starting point, but our arrow continues on forever. So it's not going to have 2 signs. We're just going to have 1. But x is greater than or equal to, so when you have domain problems on our independent activities, I do talk about that. I understand that you can't put in those signs, so you're still just putting in the right direction. But x is greater than or equal to 0, and it's equal to, because here we are, x is equal to 0 there. And our y, it's approaching 0, but it cannot equal 0. But it continues on forever, but it only starts, or it stops right here at this value as well. So it's confined on both sides, meaning there's going to be 2 signs, It's going to start at 0, and it can't equal 0, but it can be bigger than 0. And then it continues on all the way up into or equal to 120. So that's domain and range of graphing functions. That's really the important part. You can go in and look at these questions, graph the different functions, and try to answer these on your own. But other than that, you can go ahead and start on your independent activity.